Because basically for this principle, we want to see that we can replace this source. If we only know the radiation environment on some surface around this source, can we predict the generated field outside of that volume? And so now what we do is we can multiply by this equation by G, and then multiply this by phi. And then we subtract these two equations. And then we integrate. You can see that these two terms will go away. And now we have a volume integral of G Laplacian phi minus phi Laplacian G equals phi r prime. So this, we can use another vector identity, which is G Laplacian phi minus phi Laplacian G is the divergence of G gradient phi minus phi gradient G. And if we use the vector identity, we can know that this will break into two terms. And divergence of this will also break into two terms. And two of them will cancel each other, and it will be left with the Laplacian of phi, and the other two will be the Laplacian of G. So the reason we do this is, again, we can use the Gauss theorem. So now we can see that the phi prime can be written as a surface integral of G gradient phi minus phi gradient G. So what this means is that, say I have a source here, and then I have this surface S. By the way, these phi are at R. So if I write this out, it will be R. And then if I have this surface of S, then if I have a point at R prime, to find this field at R prime, we only need to know the field on this surface, and then the Green's function and the gradient of the Green's function. And that's what Huygens principle means, because to find a field point here, we don't need to know exactly what the source is, but as long as we can know the field on some surface, you can still find the field generated at the observation point. So each wavefront can be considered as a new set of sources and radiate or further radiate the field. So what we need to know here is just the phi value on this surface and the gradient of phi, the normal gradient of phi. And then sometimes this is called the dipole. This is called the monopole source on the surface. But if you're careful, you may wonder why we can find the source point here only using this surface, because I need to, this surface need to be closed, right, to include this point. So there will be another surface at infinity here to make this surface closed. So there will be another surface here. But I can always make this go to infinity so that I can try to eliminate some terms here. So the assumptions we have to make are again, when it goes to infinity, it becomes a plane wave, so the del will just become ik. And the Green's function goes with 1 over r, order of 1 over r. And the field also goes with the order of 1 over r. If it's just a finite source. And then when you take a gradient, this will go with 1 over r cubic. And the surface goes with r squared. So the integral will become 0 at the infinite surface. So that's why we can find this point only based on this inner surface here.
A question about, because we still continue with the Green function, right? And diffraction. Because there is singularity for Green function at the origin point. And it implies this kind of formulation cannot be applied below the diffraction limit, for example, some wavelength structure, right?
Because the value we need for the Green's function is only on this surface. And then as long as we choose a surface that we don't have any singularity for the Green's function, that we can always apply this Huygens principle to find the far field.
So it's all, the far field is always valid, but we do not handle something is in near field from beginning to end.
So because at the beginning I have assumed this one, this means this is already outside of the source. But if you want to find the field inside of this source area, then here you cannot use 0. You will have another source term. And then that source term will contribute to the field inside of that. And that may introduce a singularity, as you mentioned.
Oh.
So in that case, you need to write out the full expression. So do this G inner product with the source, and then add another term to there. So that term will account for what's inside of the source. But normally what we consider is the radiation of the source. Then the Huygens principle is really powerful, that we only need to know the field along some surface, and then we can generate a far field of that. Okay. And then the vector is very similar, except that you have to do what we have done for the vector Green's function. Also, again, use the few times the chain rule. So let's do this vector Huygens principle. So I probably just write out the solutions for you. So this is the dielectric Green's function I mentioned earlier, and this is the electric type because I have this delta function on the right hand side. Maybe Professor Xu will mention the magnetic type later. So now we have this E field. Same thing, the E field at this point can be generated by and then again I can change this to a gradient of something. Using the gradient of something cross something becomes a dot of del cross something. And then the other term will cancel out. So basically this will generate 4 terms, and 2 of them will cancel out, and the other 2 will become like this. And then the final expression will just become so now we can see it's very similar to the scalar case, except that I have this term and this term. Where before I have the phi at the surface and the normal gradient of the phi. So now it means that I only need to know the E field and H field on this surface. Then I can generate this far field, the E field at any observation point outside of that surface. And then this sometimes you can think of as a magnetic current, the N cross E, where the N cross H we can think of electric current. So another way of saying is that if we know the current on this surface, then we can consider them as a new set of sources and generate a far field. Okay. So, and maybe I'll quickly cover the uniqueness theorem. So basically we want to see if the field generated by the same source is unique. So it is only unique when if I define this delta phi as phi 1 minus phi 2. And only if this is equal to 0 for all R, can we say that this solution is unique? So again, we can do the subtraction, then we can find that plus k squared equal to 0. And then we will do the volume integral. If we dot this with delta phi, and then do the integration, we can have dv delta phi that's conjugate. And again, use the same chain rule to move this del to here, but the other one will be a divergence of will become a divergence of this. So this will go away, and then this term will just become gradient of delta phi dot with gradient of delta phi plus So finally, I can arrive at this equation. You can see that this is purely real, right? That means, and this is real. And from here we can say that dv imaginary part of k squared times this delta phi squared equal to 0. Oh, the way we get rid of this part is to say that there are a few conditions. Number one is that if delta phi is equal to 0 on S. A second way is to make this gradient of delta phi, normal gradient of delta phi, equal to 0 on S. The third way is a combination of 1 and 2. So you can have partially phi, partial S. Part of the S have delta phi equal to 0, and then a part of the S have normal gradient of delta phi equal to 0. That's also okay. I can still make this divergence equal to 0 because this will become a surface integral. Right? So, and this actually means that the field are the same on the boundary, or the normal derivative of the field are the same on the boundary, or partly same on the boundary. So now, not only that, we need to have, if this imaginary part of k squared is not 0, then we can say this delta phi is always 0. So to have this solution to be unique, first you have to satisfy these boundary conditions. And secondly, you need to have this imaginary part of k to be non-zero, meaning you need to have either loss or gain. So to have the solution to be unique, you first need a boundary condition, and then you need this condition. It's called a Sommerfeld radiation condition. So if you don't have any loss or gain, then your solution won't be unique. Just like what we saw for the free space Green's function, you will always have outgoing and incoming wave. But if you put an infinitesimal loss, then you will see that only one wave will survive, and that's when you make this imaginary part of k be non-zero, and the only solution is to have this delta phi equal to 0 at all places. So uniqueness theorem says that number one, you need to satisfy the boundary condition. Number two, you need to satisfy the Sommerfeld radiation condition. Then your solution will be unique. Right. And then I believe Professor Xu will talk about the vector for